Hi everyone, Mr. Thomas here, and welcome to the very first video of Virtual Geography, and welcome to the very first video of my YouTube channel. Before we begin today's lesson, I have a question for you all. What if you dug a hole right now to the centre of the Earth, straight down? What would you expect to see? What might you find in this hole? And how might the conditions at the top of the hole be different to the conditions at the bottom of the hole? In today's lesson, we're going to look at potential answer for these questions as we investigate the layers of the Earth and tectonic plates. So without further ado, let's get started. And we'll begin our investigation by looking at a model of the Earth. So here we have a model of the Earth and the layers it's composed of. We have 4 layers. The outermost layer is the crust. We then work our way inward, going toward the mantle, the outer core, and finally arriving at the centre, which is the inner core. Before we take a look at these layers, there's an activity that you can do at home alongside this video. All you need is one single hazelnut confectionery. That is the Ferrero Rocher. All you need to do is cut that hazelnut bad boy in half so you can see a cross section of it. Once you've done that, voila, you're ready to go. As you watch the video, think about how there's similarities between a Ferrero Rocher and the Earth, and think about which parts of the Earth are represented by the Ferrero Rocher. We're going to take a look at this at the end of the video, so don't eat it until the end. So our journey begins at the centre of the Earth with the inner core. There are 2 notable aspects about the inner core. It's incredibly hot and it's incredibly solid. So as I've just said, the inner core is incredibly hot. It clocks in at about 5,000 degrees Celsius, which is about 9,900 degrees Fahrenheit. It accomplishes this incredible thermal feat through radioactive decay. The inner core is primarily composed of iron and nickel. However, there are nuclear elements such as uranium and thorium. Like an atomic Jenga tower, these atoms of uranium and thorium break down over time, and when they do, they release incredible amounts of energy. When I say that these atoms release a huge amount of energy, I really do mean it. For reference, the United States in 2005 consumed 3.34 trillion watts of power, whereas the decay of thorium and uranium within the Earth's core produced 6 times that amount, around 20 trillion watts of power. This energy heats the planet's core and subsequently leads to convection currents, which we're about to talk about in just a moment. The second aspect of the inner core that you need to know about is how the inner core is still solid, which leads me on to this question. The inner core is mainly composed of iron and nickel, and the temperature required to melt these elements is 1500 degrees and 1400 degrees Celsius respectively. How come it's still solid? In essence, the outer layers of the Earth are actually keeping the inner core solid, despite the fact that the temperature of the inner core is nearly 5 times hotter than required to melt these elements. The incredible pressure put on the inner core by the outer layers pushes all the atoms together, compressing them and keeping them in a solid state, preventing them from going into a molten form. So there you have it. That's the inner core in a nutshell. It's both incredibly hot and incredibly solid, despite that incredibly high temperature. That was a lot of incredible then. So we're moving on up to the outer core. I don't know why I had to sing that. I'm just, we're going to leave it there. So we're moving on up to the outer core. The outer core shares many similarities with the inner core. Both are made of primarily iron and nickel, and both are incredibly hot. However, there is one key difference between the outer core and the inner core. The outer core is liquid, unlike the solid inner core. It's not under enough pressure to force its atoms into a liquid state, so its high temperature melts it and keeps it in a molten state. However, this does have a really, really beneficial secondary effect for us humans living on the planet. As this outer core is molten, movement can take place there. The Earth's rotation generates the Coriolis force, and differences between the metals generates motion and swirling. As this metal swirls and moves, it generates an electric current. This electric current then generates a magnetic field. The swirling outer core produces many magnetic fields, though they are all aligned by the Coriolis force. This alignment causes them to combine and create one huge magnetic field that encompasses the whole Earth. We call this the magnetosphere. So our third layer is a big layer. At approximately 2,900 kilometers thick, the mantle is the thickest layer of the Earth. The mantle is composed of hot molten rock we call magma. Like the outer core, this magma is a liquid and so allows movement to take place. This movement comes in the form of convection currents. Convection currents form when magma close to the Earth's core begins to heat up. This causes it to become less dense than the magma surrounding it, and so it begins to rise towards the surface, aka the crust. As the magma reaches the crust, it then begins to cool down. This causes the magma to become more dense and then begin to fall again. As it sinks back towards the core, it starts to heat up once again, and this creates a cycle, as you can see, of heating and rising and cooling and falling. These cycles we call convection currents, and these are what drive the motion of the tectonic plates which make up the crust. So we finally make it back home to the outermost layer of the Earth, the crust. So the crust is made of solid rock. It ranges from about 0 to 60 kilometers in thickness, making it the thinnest part of the Earth. This rock is either continental rock, such as granite, or oceanic rock, such as basalt. Oceanic crust is actually denser than continental crust, meaning that when they collide, it will actually subduct, which means go underneath the continental crust. So the crust isn't one solid, uniform layer of rock. It's actually broken up into massive sections of Earth we call tectonic plates. These tectonic plates are usually either continental or oceanic, depending on the rock that they're made out of. These huge tectonic plates make up the face of the Earth, and they cause the continents to slowly drift over millennia. It takes millennia because they are so awfully slow, about 2.5 centimeters of movement per year, which is about an inch a year of movement. These tectonic plates are pushed by the convection currents underneath them, which drives the direction that they move in. The pushing of the convection currents causes the tectonic plates to collide, subduct, and even to part away from each other. There are 4 types of boundary where these plates will meet, and that will be the topic of the next video in our virtual geography series. And so with that said, that ends our journey from the centre of the Earth and back. Now let's take a look at our hazelnut delight. So let's examine the Ferrero. Which parts of the Ferrero Rocher represent the different layers of the Earth? Firstly, let's look at the hazelnut, which is a solid mass found at the very centre of this banging confectionery delight. This is much like the inner core, which is a solid mass found at the very centre of our planet. So next up is the chocolate mousse layer. I think it's mousse? The gooey chocolate liquid layer that surrounds the hazelnut. It's both liquid and it's the thickest part of the Ferrero Rocher, much like how the mantle is a liquid and the thickest part of the Earth. Finally, we come to the bumpy exterior of the Ferrero Rocher, which is the thinnest part of it. It's very similar to our home layer, the inner core. I'm joking, it's very much like the crust. The bumps are very similar of the mountains that we have, and it's also the thinnest part, just like the crust is. If you want, you can now eat the Ferrero Rocher. If you don't want to, send them to me. I love them, they're the best. And that is the end of today's lesson. If you'd like to consolidate some of your learning, there is a worksheet and answer sheet in the description below. But with that being said, it's time for you to pack up, subscribe to the channel, and I'll see you in the next virtual geography lesson where we look at the tectonic boundaries and their characteristics. But for now, dismissed.
Hi everyone, Mr. Thomas here, and welcome to the bloopers section of my video. This is a section I like to tack onto the end of all of my videos just to prove to you learners at home that it is okay to make mistakes sometimes. It's through mistakes that we learn and we get better, and without practice, you can't be perfect. I'm a geography teacher, and sometimes even I mess up the geography. So here's a nice little bloopers section showing you all the times I messed up making this episode. So without further ado, please enjoy.
In today's lesson, we're going to look at a potential answer for these questions as we investigate the layers of the Earth and the tectonic plates that comprise the crust. We'll begin our investigation by looking at a model of the Earth. Why am I chucking it a bit? What am I doing? Before we take a closer look at these layers, there's an activity that you guys... So as I've just said, the inner core is incredibly hot. It clocks in at about 5,500 degrees Celsius, which is about 9,900 degrees Fahrenheit. It accomplishes this amazing thermal feat. It's that thermal feat that's so difficult to say. With 5,000 thermal... I keep messing them up! We'll begin today's investigation by taking a look at the model. Oh, I'm looking at the screen again. This is so hard. This energy heats the planet's core and Oh, I was looking over there. I'm looking at the screen again. Stop! Moving on up, moving on up, moving on up. I'm getting steady, moving on up. Oh, I did it! Woo! Okay. The outer core isn't a liquid. It is a liquid. It literally is a liquid. That is the one difference. So the outer core is in...